All right, howdy folks. Welcome back to Professor Carbon. This will be our first video after the summer break, and so it's a real treat to be back to just go over some more advanced topics in organic chemistry. This semester I'm actually teaching the graduate course, and so you'll see a lot of the questions are going to be much more advanced than last semester, which is also both fun, but hopefully not too intimidating to some of you. So please just feel free to follow along. As a couple of quick reminders, remember on the Professor Carbon channel, you'll notice that all of the questions are color-coded, and you can see both by functional group and topic what are the kind of key criteria in any given video. So that makes it kind of cool. And don't forget, our playlists are all organized. So if there's a particular topic that you would like to cover exclusively, feel free just to find that playlist. All right, today's question, we're going to go over these two reactions shown here, and we're just going to basically have to address some questions regarding selectivity. And selectivity is personally one of my absolute favorite things about organic chemistry because it's very challenging to get one functional group to react in the presence of a very similar second functional group. But here we'll see how some very subtle differences between seemingly identical functional groups can have a very big impact on their overall reactivity. So the first question here has to do with which alcohol reacts, and we'll notice that the starting material is a diol. It has two different alcohols. Now, some of you may remember from other work that in general, primary alcohols with two H's are generally more reactive than secondary alcohols, that have, and here R and R prime are just representing carbon groups that kind of extend the chain. And so this would be a primary alcohol, secondary alcohol, and then we can have a tertiary alcohol where all of the groups are substituted. And in general, the primary alcohol will be the most reactive. Now, in this particular case, both of these alcohols, and we check that by looking at these adjacent centers, are primary alcohols. And so we cannot use that as the distinguishing feature. But thankfully in organic chemistry, sometimes things are quite subtle, and so we can go even a step further than that. So I'm going to hop over to the green pen here. What we'll notice is the second carbon out here is a secondary carbon, and that is a carbon bound to two other carbons. And if we go here to a second piece out, now that carbon is a quaternary carbon or a tetrasubstituted carbon. That is, that carbon is bound to four different carbon atoms. In this particular case, we can refer to this alcohol then as being neopentyl. And that gets its name from this parent alcohol, which is called neopentyl alcohol. And here the CH2 makes it a primary alcohol, but because it's adjacent to this big terbutyl group, this neopentyl alcohol turns out to be a very slow alcohol to react as a substrate in various reactions. So what we're going to find out is due to the steric environment around this alcohol being all these wonderful flanking groups, the primary alcohol up here in top will be more reactive. And this means that if we choose our equivalents appropriately with only one equivalent of a reagent, we should be able to get that dangling primary alcohol to react preferentially over the neopentyl alcohol, which is exactly what's going to happen. So the desired or actual product of this reaction now will be the OTS group. Now, some of you may have forgotten the abbreviation TS, and it stands for tosyl, which is amazingly enough an acronym. So in a lot of ways, TS is an acronym of an acronym, which of course doesn't make any sense at all, but here we are in organic chemistry. So this whole piece here is TS, and so this would be tosyl chloride, and the corresponding tosylate, which is what we would refer to the product of this reaction, would be this intermediate or species, and here R is going to be the rest of the molecule shown here, so R. And so we have an O-tosyl group. And if you're curious, the reagents are triethylamine, which is a nice base, because overall the stoichiometric byproducts of this reaction are going to be the chloride and then the OH. And so we're going to make triethylamine HCl is the stoichiometric byproduct of this reaction. And DMAP, if you're curious, is dimethylaminopyridine, which is kind of an unusual reagent if you haven't seen it before. And in this case, it's going to be an additive to help catalyze or promote this reaction. If you'd like to learn more about DMAP, I encourage you just to look it up on the internet, use Wikipedia or some other organic chemistry source. All right, so that sums up the top part here. The second question here is going to be a very challenging one as well. And so right off the bat, it's telling us that there are 3 different double bonds in this molecule. And so we can identify those as being 1, 2, and 3. And, you know, all of these alkenes under some other conditions might be reactive. And so we have to identify what makes one of them more reactive than the others. In general, terminal alkenes, and I'm going to just change colors here. Terminal alkenes tend to be less reactive than cis alkenes. Ooh, I'm forgetting one in there. Forgetting 1,1 disubstituted alkenes, where we have the groups on the same side, tend to be less reactive than transalkenes. And depending on the exact conditions, sometimes cis and trans can be reactive, or you know, the reactivity can be inverted. So for here, we'll say that they're similar, which is not technically true. A lot of reagents can differentiate them, but it becomes a little bit more specific than this general trend. In general, then, the tetrasubstituted alkenes, which seem out of place, but because there are so many R groups, tend to be very sterically congested. And so as a general rule, those tend to be even less reactive than trisubstituted alkenes. But if we think about it, in most of our reactions that we look at, the alkene is a nucleophile which interacts with some electrophile. And here, that electrophile might be bromine. So hopefully many of you have already seen how alkenes can undergo a reaction with bromine, or it could be some very strong acid, some HX reagent that might make a carbocation. The moral of the story is that in most cases where the alkene reacts, that double bond pair of electrons is actually the reacting electrons. They're the nucleophilic lone pair. But there is a big difference then when we put an electron withdrawing group on that alkene, and probably one of the most famous examples of this is methyl vinyl ketone. And we know that these alkenes are actually pretty good electrophiles. And they're pretty good electrophiles then because you can have an enolate as the result of an addition reaction to them by that nucleophile. And so this is a very different sort of alkene then, where these alkenes with an electron withdrawing group are actually electrophiles, whereas all of these alkenes without that electron withdrawing group behave as nucleophiles. And so they're fundamentally different. So what I encourage you to do when looking at these alkenes up top is to identify them either as being nucleophiles or electrophiles. And in this case, this one would be nucleophilic, this one would be nucleophilic, and this one would be electrophilic because it has not 1, but 2 double bonds next door. So overall then, what we can imagine doing, or what we can discover, is what sorts of reagents we have here, and this will help us identify the complementary reactivity. As it turns out, sodium carbonate is a base, and it is going to react with hydrogen peroxide to make the hydrogen peroxy anion shown here. And this anion is a really good nucleophile. And it's a really good nucleophile for a couple of reasons, one of which is it's relatively small. The second of which, though, is the oxygen lone pair on that first oxygen is going to have some lone pair repulsion on the second oxygen. And so that's going to focus the orbitals a little bit more and make it more nucleophilic than hydroxide would be all on its own. And so since this is a nucleophile, then we want to partner it with an electrophilic alkene. And so we can imagine this attacking that alkene to make an enolate anion. Ultimately, that enolate anion will come back and attack the peroxide. And so I'm just going to cut ahead here real quick. What we're going to end up with at the end of all of this is an epoxide. Oops, got to get one more bond in there. Something like this product. Now, there's something else that's really cool here. So, but this, by the way, is the correct product. And alkene 2 circled up here is going to be the one that participates. And it's going to participate again because it's an electrophilic alkene, not a nucleophilic alkene. The product, if we check, has 1 and 2 additional new stereocenters. And it turns out on this particular reaction, you're going to get full selectivity for one product over the other product. And so this is actually going to be very cool. And the phenomenon that's going to occur is that these bridging H atoms are going to make this overall ring system somewhat cup-shaped, with the H's kind of sticking out on top. And then the chemistry is going to prefer to happen from the outside face instead of the inside face because there's steric blocking. And so this is something that is referred to as concave convex differentiation. And so overall, what this means is that we're going to be able to get a really fun product out that is a single isomer. So not only are we going to end up having one alkene react instead of the other 2 alkenes, we're going to be able to get full stereoselectivity. And so in this particular case, the nucleophile is going to attack from the same face as these H's. And so we're then going to have our wedge epoxide here. We'll have an H going down, and then we'll have another H going down for this 5-carbon chain, which, if you care, is called a prenyl chain. And so there you go. Turns out that prenyl chain pops up in a lot of other natural products and other molecules of biological interest. And so that's kind of fun. All right, so thank you again for tuning in to Professor Carbon. Just as a reminder, please do subscribe to our YouTube channel. It's really been a treat watching that number slowly tick up throughout the spring semester, and then hopefully it'll begin to accelerate here the fall semester as more students discover us as we're still under our COVID lockdown situation. And so with that, thank you for your attention. Please tell your friends all about us.